You know, if you've ever been anywhere near the world of software development, you've probably heard the most infamous excuse in the entire industry. It's a phrase that has torpedoed projects, started arguments, and just caused so much frustration. But what if I told you that entire problem, a problem that plagued computing for decades, was solved by an idea inspired by, of all things, the humble shipping container? Yeah, really. Let's get into it.
All right, so here's our game plan. We're going to start with that software nightmare I was just talking about. Then we'll look at how containers came to the rescue. We'll dive into the magic that makes them work, peel back the curtain on something called kernel versus user mode, see how they're actually built, and then wrap up with why this whole thing has completely changed the game for modern technology.
So, first things first. Before we can really appreciate just how brilliant the solution is, we have to feel the pain of the problem. We need to understand the chaos.
Ah, there it is, the classic. A developer writes some code, it runs beautifully on their laptop, everything's perfect. But the second that code gets moved to a test server, or heaven forbid, the real live production server, it just crashes and burns. So why does this happen? Well, it's because the environments are totally different. The developer's machine has one version of a library, the server has another. Maybe there's a configuration file that's slightly off. It created this massive, unpredictable headache that made shipping software a total nightmare.
And this is where our hero, the container, enters the story. To finally solve this problem of messy, inconsistent environments, the tech world basically borrowed an idea from global shipping. The big idea here is all about packaging. It's simple, really. Instead of just sending your application's code out into the world by itself, you bundle it up with everything it needs to survive. All the right libraries, the exact configuration files, every single dependency. You put it all in one box. And that self-contained, predictable little bundle is what we call a container.
And you can really see the difference right here. On the left, you've got the old way. The app is just sitting on the operating system, totally dependent on it. If the OS has the wrong version of something, poof, the app breaks. But look at the right. The containerized app brings its own little world with it. All its dependencies are tucked safely inside the container. It's totally isolated. This guarantees that if it runs on the developer's laptop, it's going to run exactly the same everywhere else. Problem solved. Okay, so how does this actually work? Is a container just like a tiny computer running inside a bigger computer? Well, that's what a lot of people think, and it's a really common misconception we need to clear up right now. And this is the question, right? It gets to the very heart of the innovation here. A lot of folks hear isolated environment and immediately think of a virtual machine, or a VM. And yeah, they do a similar job, but the way they do it is fundamentally different. And honestly, it's way, way more efficient. This table lays it all out perfectly. A virtual machine on the left, it has to virtualize the actual hardware. That means for every single VM, you have to install a complete separate operating system. That's why they're massive, we're talking gigabytes, and they take minutes to boot up. Now look at the container. It does something called OS virtualization. And check out that highlighted part. It shares the host OS kernel. It doesn't need a whole guest OS. That one difference is why containers are so tiny, just megabytes, and why they can start up in seconds. But what on earth does sharing the kernel actually mean? To get that, we have to pop the hood on the operating system itself. We need to look at a little secret for how it protects itself from all the different programs it's trying to run at once. Okay, so the kernel is the absolute brain of the operation. It's the master controller, the boss. It manages the CPU, the memory, the hard drives, everything. And because it's so powerful and so critical, the system has to put a big wall around it. You can't have some random buggy application crash and take the entire computer down with it, right? So to create that wall, modern processors have at least two different modes. First, there's user mode. This is where all your normal apps run. Your browser, your music player, you name it. It's a restricted area. A program here can't do anything dangerous, like directly messing with hardware. Then you have kernel mode. This is the VIP section, the inner sanctum where the OS kernel lives. It has privileged, unrestricted access to do literally anything. This split isn't just a software trick. It's a security feature built right into the hardware. So what if an application in that restricted user mode needs to do something important? Like, say, save a file to the disk. It can't just barge into kernel mode and do it itself. So instead, it makes a formal, polite request to the kernel. This request is called a system call. It's basically the application knocking on the kernel's door and saying, "Excuse me, could you please do this sensitive task for me?" And here's exactly how that little dance works. Your app in user mode needs something done, so it triggers a system call.
The CPU then carefully switches from user mode into the powerful kernel mode. It hands control over to the OS, which checks the request, makes sure it's safe, and then does the work. Once it's done, the CPU switches right back to user mode, and your app continues on its way. Now, this is the magic behind containers. The container engine uses system calls to ask the host kernel to create these little isolated bubbles using Linux features like namespaces and C groups. It essentially tricks each container into thinking it has its own private machine, even though they're all just sharing that one single kernel. That's the secret sauce to all their efficiency.
Okay, so we get the theory. We've gone deep into the OS. But how does a developer actually make one of these things? Let's walk through how you get from a line of code to a running container. It's a pretty straightforward four-step process. First, the developer writes a simple text file, kind of like a recipe, that says, here's the base system I need, here are the libraries to install, and here's the command to run. Second, they use that recipe to build an image. Now, this is a key distinction. The image is a static, read-only blueprint. It's not the container itself. Third, they push that blueprint, that image, up to a central library called a registry, so anyone on the team can grab it. And finally, step 4. You run the container, which is a live, running instance created from that static image. And you can spin up thousands of identical containers from that one single image. All right, let's zoom back out. We've gone from the problem all the way down into the technical weeds of the solution. But what's the big picture? Why has this one idea become so fundamental to pretty much all of modern computing? Well, the benefits are just massive. Portability, it finally solves that it works on my machine problem for good. Speed, we're talking about applications starting in seconds, not minutes, which makes developers ridiculously fast and agile. Efficiency, you can pack way more containers onto a single server than you could VMs, which saves a ton of money. You get perfect isolation, so no more dependency conflicts. Operations gets way simpler because now everyone is just managing one standard thing, the container. And all of this leads to insane scalability. You can launch new containers almost instantly to handle a sudden rush of users. This technology is the engine behind microservices, the cloud, you name it. So in the end, by creating this universal package for software, containerization brought order to the absolute chaos of software deployment. It standardized how we build, ship, and run our applications across the entire globe. And that really leaves us with one last big question to chew on. After a revolution this huge, what's next? What's going to be the next fundamental shift that changes how we think about computing all over again?